Okay, so I am now on level 2 to level 3 of the Narnia war game. So I SSH'd into the Narnia server and we can cat the code for the challenge. And this is the code. So I think it's much shorter than the one last time. But all it does is that it accepts a string as argument. It copies it into this buffer, which is 128 bytes, and then prints it out. Simple enough. So if we try to run it, let's do Narnia 2, and it just, maybe you can't see right now, but if I do Narnia 2, hit it with 4 A's, we get 4 A's back. If I, let's clear, if I try to make this very long, maybe at some point we'll get a buffer overflow, probably after 128 characters. Okay, there we go. See now, segmentation fault, core dumped, which means that we overflew the buffer. So just like last time, let's make a Python script, which is going to help us craft an input. That's going to be a lot easier than like trying to count all those A's by hand or whatever we end up putting in there. Let's vim import sys, and then write is sys dot std out dot buffer dot write. And now if we write x for 1, let's do this like times 4. If you try to write 4 A's, let's see if this runs. Okay, so now we can print out 4 A's using raw bytes. So I have the code opened in another tab to make it easier. So the buffer is 128 bytes, meaning if we go in our script, we could put 128 A's and it shouldn't overflow. Yeah. So up to 128, it's not going to crash. And let's see how far we can go until it crashes, because that's going to be pretty interesting. And let's go by increments of 4, because we basically know after we overflow the buffer, what we're going to be overriding is the base pointer of the old stack frame, and then the instruction pointer that we're supposed to return to after we return from main. So since these pointers are going to be 4 bytes, we can increment this number by increments of 4 until we get an overflow to see like what needs to get overridden. Like there's no point in going increments of 2 because we know that whatever we're going to be overriding is like chunks of 4. So let's do times plus 4 times 1 for now. And let's see what that gives us. I guess it's not valid. 128 plus 4 times 1. So I guess it crashes after the first, if we override 4 bytes. Okay, let's go by increments of 1. Maybe I try to rush things a little. Let's do 30 and then see what happens. So 30 works. I'm running it multiple times just to make sure, like, you know, it's not a fluke or something. Okay, that seems to work. Let's go back in our scripts. Let's do 32. Theoretically, that should bring us back to where we were. Okay, core dumped. I was expecting it to crash after 8 bytes because we know that after we override the 128 bytes, the next 4 bytes we're going to override are going to be the base pointer, and then the next 4 bytes are going to be the instruction pointer. But I guess it crashes even when we override just the base pointer. Let's confirm our hypothesis using Radaris. So what I'm going to do, we're going to call this buffer, and we're going to override the buffer with a bunch of A's, 128 A's to be exact. And then we're going to put the base pointer and we're going to put B's times 4. And then EIP, which is the instruction pointer, and we're going to put C's times 4. Let's write the buffer plus EBP plus EIP. And let's see if we manage to override the correct things. So let's run it. We get a sec fault. But now what if I open this in Radare? We're going to seek main. Right when we leave, I'm going to put a debug break. Let's continue, hit the breakpoints. Okay, let's check what our stack looks like right now. Yeah, okay, so because that's right, that is what is right under our stack. Because anything we see right here is right under our stack. And what if I do ESP? Okay, so now we can see our stack. So our stack is all of this, which is basically the entire buffer, because that's the only thing in stack right here. Right after we have the 42 and the 43 that which is our overflow. And what we have to figure out is what register these things go in. Let's step. We want to see after we return, step. After we return, we're on 43434343, which means that it's going to start executing whatever is at 43434343, which doesn't exist, right? If I PDF, there's no function here, there's no code, because this is like a random bullshit address. And if we look at our registers, we can see the base pointer that got overridden. All right, I don't know if we can see it here. I hope it's not hidden. But yeah, this is what we expected. So how is this hack gonna work? What we're gonna do is we're gonna inject some shell code, which is going to spawn a shell. And conveniently, we can just use the same shell code as last time because it seems to work. So, you know, if it's not broke, don't fix it. It was this one. It was shellcode 607. So I'm guessing we could just reuse this shellcode because it seems to work. So I'm going to copy this and put it in the script. But before that, I'm going to explain what we're going to do. We're going to overflow the buffer with no ops. Well, we're going to fill the buffer with no ops. And then after that, we're going to override EIP, the instruction pointer, to point to somewhere in the buffer so that we can start executing code. So for now, it's just going to execute no ops, but somewhere in the buffer, I guess at the end of the buffer, we're going to put our payload. So let me open up draw.io. This is our buffer, which is 128 bytes. And after that, we have two registers that we can overflow, which is EBP, which is 4 bytes, and then EIP, which is 4 bytes. Now, EBP, we don't really care about. We can override this with anything. But EIP, we need to make it point to somewhere in the buffer using like the memory address of somewhere in the buffer. And we can place in the buffer, at the bottom, we can input our shellcode. And then the rest of the buffer is going to get filled with no op, which basically means like don't do anything. After we return from our function, we're going to start executing a bunch of no ops. And then we're going to hit our shellcode, which is going to spawn our shell with the user Narnia 3. So basically do a privesc. Now we could just skip all the no ops and point directly to the start of the shellcode, but that could be annoying to do if we don't know the exact memory address that the shellcode starts at. So one pretty common tactic, it's just to use no ops. That way we can hit anywhere within the buffer and it's just going to slide down the no ops until we hit our shellcode. So let's go ahead and craft that. Paste that in here. We know that the buffer is 128 bytes. So we want to fill no op to be hex 90 is the code for no op, and we want to have that 128 times minus the length of the shellcode, because we want the no ops to fill everything in the buffer except the shellcode. Then I want my nop slide. Let's call this nop slide plus the shellcode. So these two together is going to equal exactly 128 bytes, which means it's going to fill up the entire buffer right here. And then after that, we can override the EBP and the EIP. So the EBP can be anything. So I'm just going to put, I don't know, I can just put A's. It doesn't really matter. There just needs to be 4 of them plus EBP. And then I need my EIP. So I don't know what the EIP is going to be yet, but I'm going to use Radare to help me with that. So EIP, I'll just put a bunch of C's in right now, and then we'll go ahead and fix that later. EIP. So if we run this without Radare, what do we get? We're gonna get a core dump because EIP is invalid. Okay, let's open this in Radare. Let's seek main PDF. We're gonna put a debug break on here. Debug continue. We hit our breakpoint. Debug. Well, we can go at ESP. Oh, I think I went too far. Okay, I think we need a debug break a lot earlier before we hit the leave, before we leave the stack frame. So I'm just gonna put a debug break right here, and let's reopen. Debug break right here, debug continue, and now ESP. Okay, so we can go anywhere within our NOP slide, and this is the NOP slide. We know because there's a bunch of 90s, and after the NOP slide is where our shellcode starts. So the shellcode starts with EB11. If we check online, EB11, yeah. So that looks all correct, and I can just take any of these addresses, and it's gonna start executing from here. Go down the NOP slide until it hits our shellcode. I'm just going to take this one. So you want EIP to be this, FF, D2, A4. But because we are in Little Endian, it needs to be backwards, meaning it needs to be hex A4, X D2, X FF, X FF. So the A4 corresponds to here, D2 here, and so on. But it needs to be backward. That's very important, or else it won't load. Let's run our script. Hopefully this works, or dumps. Let's open this in Radare. Let's see what's going on. Okay, so let's debug break here. Debug continue. Now if we debug step, we should be at this address. And if I PDF, why is there no function? What if I PX at here and see what's going on? So it should be 90. I don't understand how that's not a function, because that is code. Oh, is it because we're too off? Because it needs to be like, maybe it needs to be aligned a certain way, and so we're like in the middle of some alignment, so it doesn't align perfectly. A2, A4. Because see, if we align with like A3, for example, maybe this is better. That's weird. Let's try A3. But I feel like if there is an alignment, it would want like an even number. So I don't understand why A3 would work. But let's try it. Well, what if we try to PDF at here? Okay, let's try it. A3 segfault. What if we aim directly at the start of the shellcode? I really don't understand how the NOP slide does not work. Because if I try to print two instructions at here, for example, see, we see NOP, like this should be valid. Debug step, debug step, debug step. And now we go here, and then if we PX, at the current address, we see this. If I PX two instructions, NOP, like, I really don't get it. I guess it is going down the NOP slide. I don't get how there's an error though. I don't understand. Okay, I'm gonna try to put the address where the shellcode starts to see if we still get the same error. So it starts like this. EB11, whatever, and it keeps going. Let's try this. Let's run segfault again. I'm so confused. Okay, so I had to take a break for a little bit because I really ran into some problems and I could not understand for the life of me why it wasn't working. And as you can see here, I managed to make it work. So for full transparency, I went on this website right here, and it uses like a similar exploit, meaning that it's like a string copy that is vulnerable. But anyways, what was missing, see, if I go here, you could see that my effective ID is Narnia 3, meaning that we can actually read the password now. But if I go back to my code, you can see that what changed is that we inserted some padding. So what that means is that instead of the shellcode being directly at the bottom, what we did is that the shellcode is now somewhere in the middle of our buffer, and we have some padding at the bottom. So in my example, my padding is just a bunch of knobs too, but I don't think it really matters what this is. So the shellcode is in the middle, and then the exploit is basically the same, right? We just point somewhere at the top right here, and then then when we execute the code, it'll execute the shellcode. But the main difference is that the shellcode actually uses pop and push and tries to build things on the stack. And so if you don't have a padding right here, your code's gonna bug out because it doesn't have enough memory to execute the exploit, if that makes sense. So that's why you need some padding. In my example, I tested it with 10 and it didn't work, and now I'm testing it with 40 and it does work. Let's try 30. Like I'm sure there's like a point at which it doesn't work anymore, but that's what was missing. So when you're doing these types of stuff, always make sure to have padding at the bottom, because this code right here, like the polymorphic execve, what polymorphic means is that this code will modify itself. So as it's running, it'll modify the code itself using the stack, using push, pop, and all that stuff. So if you don't have enough padding right here, you'll be pushing into like EBP, EIP, and then it's going to make your code crash. So you don't want that. You definitely want some padding. I changed my padding to 30, and now let's see if it runs, and it runs again, right? Let's change it to 20, see how much padding we really need. Okay, so I guess 20 is not enough. I'll try 25 and then I'll stop fooling around and I'm going to end the video. But yeah, if I run this ID, I am Narnia 3, meaning that I can cats Narnia 3.c. Okay, yeah, so I can see the code for the next challenge, and I'm going to go ahead and record the password for this. I'll make the next video soon, hopefully. And yeah, I'll see you guys in the next one.